Okay, it's similar to mx double dot plus kx equals 0, but then instead of, so x is analogous to theta, but instead of x, we have sine theta here. Here we have x double dot, here we have theta double dot, but instead of x, we have sine theta. So what we can do is use a small angle approximation. Or a linearization. Which is to say, for small theta, we have sine theta approximately equal to theta, or the Taylor series of sine theta about theta has theta about theta equal to 0 has theta as the first term. Okay, so we say, so replace sine theta with theta, which is an approximation, of course, right? An approximation that is only true for small angles theta. So we get theta double dot plus g over L, theta equal to 0. Okay, so this is the linearized equation. It's linearized because sine theta is a nonlinear function, and we've taken that and replaced it with theta, which is, of course, a linear function of theta. Okay, so this is called a linearized equation or a linearized differential equation. And now this one is completely analogous to mx double dot plus kx equal to 0, where instead of m, we have the number 1. Instead of k, we have the number g over L sine theta, right? So in fact, if we can sort of more analogously write this as x double dot plus k over m x equal to 0. So let's just write that here. Analogous to, exact correspondence with, mx double dot plus kx equal to 0, or x double dot plus k over m x equal to 0. So what this means is that for this equation, so let's call this equation 2. For equation 2, this is equation 2. Let's call this equation number 3. For equation 3, omega n is sort of analogous to k over m. You just go square root of g over L. Okay, that's it. And then time period, you can go fn equals omega n by 2 pi, or tn equals 2 pi by omega n, etc. But this is the key relationship that we get for simple pendulum, where the frequency or the angular frequency is dependent on the length of the pendulum and the gravitational constant. It's inversely proportional to the square root of the length of the pendulum, where if you make the length shorter, the frequency increases. Shorter pendula oscillate faster. And more importantly, it is independent of the mass of the pendulum, because the mass sort of gets cancelled. So that's it. So that's how for other systems, like for instance a simple pendulum, you can essentially use all the things that we derive for this equation by making essentially correspondences with it's the exact same equation except with the constants replaced and the variables replaced or renamed. So the exact same derivations apply, so you can just use the same formulas as before. You can sort of think of this as a stiffness and this as a mass, or actually in this case, this is a rotational stiffness and this as a rotational inertia. In any case, you can make these correspondences with the coefficients here and here, here and here, and you get these formulas. That's it.